Okay, I have typed up these notes because I haven't seen anybody present it exactly like I do, and I kind of like my 4 guidelines for solving logarithmic and exponential equations. So each Roman numeral here is what I call a guideline. For example, guideline 1 tells you what to do when there's only one log in the problem. So if there's only one log in the equation, rewrite it as an equivalent exponential equation and then solve using the definition of logs. In order to do that, you have to remember the definition of logs, which is y equals log base a of x if and only if a to the y equals x. So here's our first problem. We want to solve log x plus 2 equals 3. What is the base of this log? So the base of the exponent will be 10. 10 raised to what power? Equals, and 10 to the third is 1,000. And then subtract 2 from both sides. So x is equal to 998. So can we check this on our calculator? Sure you can. It works. So that's the solution to this problem. So if there's only one log in the equation, even if that variable is by itself, you can use the change of base formula. But if you don't know what to do, rewrite the log as an equivalent exponent. Next, we have the one-to-one properties. Do you remember the one-to-one properties for logs? If log base a of x equals log base a of y, then x equals y. Or if log base a of x equals log base b of x, then a equals b. And also for the exponents, if a to the x equals a to the y, then x equals y. So when you have a log equal to a log, or you have an exponent equal to something that you can write with the same base, then you can solve these using the one-to-one properties. And they're kind of nice. So if we have 81 is the same as 3 to the 4th, so this becomes 3 raised to the 2x equals 3 to the 4th, so 2x is equal to 4. Because we have this situation where the bases are the same, so we could just set the arguments equal to each other. Or you could say you're taking a log of base 3 of both sides and that gets rid of it, but hey, that's not necessary. So what is x going to be equal to then? 2. Right here we have a log base 5 of 3x equals log base 5 of 12. 3x equals 12, so what is x equal to? Here we have a log base x of 7 equals a log base 3 of 7. What is x equal to? Using the one-to-one properties. And if you have a log equals to a log, that's what you want to do. One log, write it as an exponent. 2 logs, and they're equal, use the one-to-one properties. Guess what guideline 3 tells you how to handle? 3 logs. If the equation has several logs with common bases, this is key, you have to have common bases, and they are added and or subtracted. So we have plus or minus between the logs. Then we can use the product and or quotient rules to rewrite those logs as a single log. We just practiced doing that. Then solve using either guideline 1 or guideline 2, because one of those two will apply if you don't have pluses or minuses between logs. You're either going to have one log in the problem or a log equal to a log. Let me write down the product rule. Log base a of x plus log base a of y equals log base a of xy. That's the product rule. And the quotient rule is log base a of x minus log base a of y is equal to log base a of x over y. So that's the product rule and the quotient rule, just so you can remember. Well, if we have log base 2 of x plus log base 2 of x plus 2 equals log base 2 of this, what do we want to do first? You get rid of the addition. That tells you right there that you're going to use the product rule. So log base 2 of x times x plus 2 equals log base 2 of, and now we can just drop the logs. But I'm going to also distribute this. So that's going to give us x squared plus 2x equals 3x plus 6. What type of equation is this? Quadratic. And how do we solve quadratic equations? Set it equal to 0. So we're going to subtract 3x from both sides, and we're going to subtract a 6 as well. And that's going to give us x squared minus x minus 6 equals 0. And fortunately, this one factors. So we have x plus 2 and x minus 3. So that gives us x equals negative 2 and x equals 3. So would we then say that our answer is negative 2 and 3? Are you sure? What's wrong with what I have? You got it. Negative 2 is not in the domain of a log. Remember, logs go from 0 to infinity. See, if I'd have just told you, you wouldn't have been as likely to remember it. When you're solving an exponential equation, the domain is all real numbers. But on a log, you have a restricted domain. Remember, the domain goes from 0 to infinity. That's the domain for a log. So the negative 2 was outside of the domain. Part B. What did we notice about this problem? What rule are we going to use? So this becomes log x over x minus 1 equals 2. What rule do we use, or what guideline do we use now? Guideline 1, rewrite it as an exponent because there's only one log in the equation. So what is the base going to be? Raised to the equals. This was guideline 1. And this one, by the way, was guideline 2. So this becomes 100 equals x over x minus 1. You have a choice however you want to think about it. You can put 100 over 1 and cross multiply, or you can multiply both sides by the LCD. That's what I'm going to do. And then distribute. However you do this, you're going to get 100x minus 100 equals x. Even if you cross multiply, you get the same thing. So now what? But I'm going to subtract 100x. That'll work too. Then the reason is because I have a number over here and a variable over here. I just want to move the variables on the same side. I don't care what side you move it to. So what I have now is negative 100 equals negative 99x. How do we get the x by itself? Divide both sides by 99. Is this a valid answer? Sure it is, because it's positive. What about 100 over 99 minus 1? Is that positive? Then there would have been no solution. Good question. The question was, what if it was negative? If this number would have been less than 1, we would have had a negative in that log, so we couldn't have done it. But this one happens to be in the domain, so our final answer here happens to be 100 over 99. If it causes one of these logs, either one, to be undefined, you have to go back to the original problem to check. If it causes one of those to be undefined, then there's no solution. And no solution is a perfectly acceptable answer if that's what happens. Guideline 4. If the equation has only exponential expressions with different bases, take either the natural log or the common log of both sides of the equation and move the variable out of the exponent using the power rule. Isn't that what we did when we were developing the change of base formula? Yes, if you look back at section 5.5, when we developed the change of base formula, that's what we did. Those are the steps that are written in green over here on the video. To get a variable out of the exponent, we're going to use logs. I cannot rewrite 5 as a power of 3, and I cannot rewrite 3 as a power of 5. So the one-to-one property does not apply here. So we've got to use logs. Okay, and remember the power rule. It says if you have a log of a raised to the m, that's equal to m times the log of a. So we're going to take the natural log of both sides of this equation. So on the left, I get the natural log of the left side equals the natural log of the right side. What was on this side was 5 to the x, and over here we had 3 raised to the 2x minus 1. So when I rewrite the left side using the power rule, tell me what to write. What's wrong with this? Okay, let's use the power rule in reverse. If we don't think there's anything wrong with this, then I should be able to use the power rule going back, get back to where I was. So let's try it again. This will go up into the exponent, giving me the natural log of 5 to the x. This is 2x minus the natural log of 3 raised to the first. Why wouldn't we move the whole thing up there? Because these are two different terms. Do you see the problem? You need to put it in parentheses so that we know that this whole thing is the exponent. What you did was technically correct, but you need to put the parentheses there so that you remember that whole thing was in the exponent. Because now we have this binomial expression multiplied by a constant. And guys, when you have a binomial expression multiplied by a constant, how do you get rid of the parentheses there? You distribute. Guess how we're going to get rid of the parentheses here? We're going to distribute. So we're going to look at this as the natural log of 3 times 2x and the natural log of 3 times negative 1. So rewriting this problem now, we get x natural log 5 equals 2x natural log 3 minus the natural log of 3. This is just a plain old linear equation because we have one variable x raised to a power of 1. Would you agree with that statement? Sure. So if we have a plain old linear equation, what's the first thing we're going to do in order to solve it? Get the variables on one side, leave the numbers on the other. So what's going to move here? Minus 2x ln 3, because this is just a number, right? There's no variable there. Fight the fact that these are letters and your brain says that these are letters. I learned that in kindergarten because I told you, no, now it's a mathematical operation. It just looks like letters, but it's really a mathematical operation like the square root. So what we do to one side, we have to do to the other. So on the left side, these are going to zero out, and we're going to get negative natural log 3. But what do we get on the right side over here? Nobody's subtracting the x's. I'm so proud of you. It's x natural log 5 minus 2x natural log 3. I lined these up on purpose, hoping that you would try to subtract them, but you didn't because you remembered me saying these are not like terms. You cannot combine them. In order to be considered like terms, the variable parts have to be the same, but the arguments on the logs have to be the same as well. And y'all have seen this before with square roots, haven't you? If you had 3 square roots of 2 plus 7 square roots of 3, you can't combine those. They're not like terms. Well, the natural log 5 and the natural log 3 are not like terms either. But if I had this, now I can combine. So if the arguments are the same and the variables are the same, then you can add the numbers together in front. But if they're not, you can't. Anyway, now that we have just one variable on, we can factor out one variable on the left, and that gives us the natural log of 5 minus 2 natural log 3 equals negative natural log 3. These are just numbers. And I can divide this off and get the x by itself. What you do to one side, you have to do to the other. At this point, I'm going to move it up here, and our exact answer is this. X equals negative natural log 3 over the natural log of 5 minus 2 natural log 3. This is the exact answer. And if I ask for the exact answer, I want to see this or I want to see this. Either one of those are fine, but you've got to give me the exact answer. See, I could have factored a negative out of the denominator and canceled with that one on top, and then this term would be first, and that would be second. And 2 squared is 9, so you could rewrite it like that using your properties. I don't expect you to give me this, but you can. If I ask for a decimal answer, I'll let you tell me that x is approximately equal to what? Negative natural log 3 divided by, open parentheses for the denominator, and this is what most people forget. Don't you forget it. Then it's the natural log of 5, close the parentheses for the argument, minus 2 natural log 3. And if you don't close the parentheses here, your calculator will close them at the end. And it is 1.869, so that's going to be 1.87. I want to round it to 2 places. Now we're going to look at how to solve equations using a graphing calculator. Now these you can only get the decimal approximations for your answers. Right here, I don't know what to do with this because I have a linear expression here and an exponential expression here and a constant here, and that's just too overwhelming for me. So what we're going to do is we're going to, in our calculator, type in y1 equals x plus e to the x. And we're going to hit y2 equals a constant function 2. And then we're going to use the intersect function of our calculator. So here we go. We're going to go to y equals. We're going to type in our function. And our function here is going to be x plus e to the x. To get to the e, we're going to hit second ln. And then use our variable x. Our second equation, y2, is going to be the constant function 2. So we're going to look at where the left-hand side of this equation is equal to the right-hand side of the equation. Because we don't know what the window is going to look like, we can do a zoom 6. However, zoom 6 is your standard zoom. I have a feeling we're going to need to zoom in some. We don't really have to because we're going to use the intersect function. We could get a better picture if we zoomed in, but that's not necessary. Does everybody know how to get to the intersect part of your calculator? Second trace gives you this whole big window. And right here is what we're looking for, intersect. Matter of fact, on your notes, I'm going to show this screen. In order to get to this screen, you're going to hit second and then trace. Hit the second button on your calculator and then the trace button to get to this. And this is the one that's going to give you the intersection of your graph. I kind of wanted to put this on there as well. What I need to do is I need to actually hit second trace and go to intersect, which is number 5. It's going to ask you what is the first curve, and it gives you the equation for the first curve up here. Move that cursor over closer to the point of intersection. So I'm bouncing close to it. Hit enter. And then on the second curve, hit enter. And then it asks for a guess. We don't want that. Hit enter again. And we get this for our intersection. And that's what I actually want to put here. And there we see our decimal approximation for x. So this right here is our decimal approximation for our answer. So right here we'd say x is approximately 0.4429. So that's pretty much all there is to solving equations. If there's one log in the equation, what are you going to do? Rewrite it as an exponent. If you have a log equal to a log and the bases are the same, what are you going to do? Use the one-to-one properties. If you have addition or subtraction between logs, what are you going to do? Product or quotient rule, then use guideline 1 or 2. If you have a variable in the exponent, take the log of both sides of the equation. And then if you're going to solve this using a calculator because you can't solve it any other way, you'll only get a decimal approximation for your answer, and you use second trace. Graph the left side, graph the right side, find the point of intersection. Now you may have to adjust your window to see that point of intersection, but it can be done.